Math 10 YouTubers, Mr. Tronis here. Here we go, 2.4. We're almost halfway through this unit. Perfect squares, perfect cubes, and their roots. All right, so part of this is going to be review from our exponents unit. So perfect square, remember that is a number that can be written as a product of two equal factors, two of the same number being multiplied. So 16 is considered a perfect square. Why? Because we can write it as 4 times 4, the same factor multiplied by itself. Another one would be like 25, because we can write that as 5 times 5. Or 100 is another common one, 10 times 10. Or one that we don't often think about, but it is a perfect square that is used a lot later on in more advanced math, is simply 1 times 1. So it is technically a perfect square too. And square roots is really just a number whose square is the given number, meaning that if I take a number and square it to get 4, that means that I can go backwards and take my 4 and square root it to go back to the 2. Okay, so this again is review from our previous unit. So that means if I take the square root of 16, I can go back to 4. Okay, so these are inverse. You can square things. Okay, you can square the 4 to get the 16, or you can square root and go the opposite direction. Same as adding and subtracting, multiplying and dividing are inverses, so is squaring and square rooting. So same thing applies for perfect cubes. It just means 3 of the same number being multiplied. So 27 is a perfect cube because, again, this is 3 times 3 times 3. Another one is 8, which is just 2 times 2 times 2. And 64 we see often as well, because that's 4 times 4 times 4. And 1, again, I'm going to put in here because we see this all the time. 1 times 1 times 1 is a perfect cube. Okay, now when we take the cubed root, okay, so it looks like this, and it has a little 3 here. That's a cubed root. So we go back to that original factor. So if I take a perfect cube and cubed root it, that's the same as saying that's equal to 3. I want to write this in a slightly different way because we're about to use this. So I'm going to go back up to this 16. Recall that I can actually write root 16 as root 4 times 4. So now you can see clearly, oh, it's just the same number being multiplied by itself. To take the square root, I get back to a single factor of 4. So the same thing can happen here. If I take the cubed root of 27, I'm saying, hey, what number times itself 3 times gives me 27? Well, that's 3 times 3 times 3. So if I take the cubed root of 3 times 3 times 3, I get the single factor of 3. Now, we can use prime factorization for square roots, cubed roots, and all roots, etc., of really big numbers, okay? Because before, we'd need a calculator for this, and now you won't, because you can use a prime factorization tree or factor tree. So we're going to take this 1,296 and start breaking it into its prime factors. And because of our divisibility rules, I can see that, oh, let's try 1 plus 2 plus 9 plus 6. If I try to add those up really quick, I get 18, which is divisible by 3, but divisible by 9 as well. So I know I can divide this by 9, and that's going to give me 144. You can use your calculator to check that out. Now the 9 here can be broken up into two primes of 3 and 3, 3 times 3. 144, I know, is actually a perfect square. That's 12 times 12, but 12 is not prime. We're going to break that into 3 times 4, and 4 is not prime. I have to break that into 2 times 2, and same for this 12, 3 times 4, and 2 times 2. And now I can see I have only primes left over. I have 3, 3, 3, 2, 2, 2, 2, and another 3 here. So it is helpful to give them, circle your primes so you don't miss any. That's the most common mistake I find in this stuff. So let's actually write this out. So I have 1,296. I'm going to write it out in the long form. So first I have 4 2's. 1, 2, Whoops, that looks a little bad. 2 times 2, and then I have 4 threes. Okay, and I'm trying to figure out, hey, what is the square root? Okay, what number times itself gives me 1,296? Well, the same way I can take, like I did above, the square root of 4 is the same as saying the square root of 2 times 2. I essentially need to take all these primes, okay, and put them into two equal groups. If I can do that, then I can find the square root. And let's just rearrange them. Right now, I have my 4 twos and my 4 threes. Well, let's arrange them into two groups using brackets. If I take 2 of the 2s and 2 of the 3s, okay, and then I take 2 more 2s, the 2 left over, and the 2 3s left over, you can see now I've arranged it into two equal groups. That is crucial. Okay, what did I do here? I arranged the primes, the prime factors, into two equal groups. What does that mean essentially? Well, let's actually multiply them out and see what I get. 2 times 2 is 4, times 3. Actually, I'll show you a better way to do this. Let's just multiply 2 times 2. I'm going to get 4. 3 times 3, I'm going to get 9. And I get the exact same thing over here. 2 times 2 is 4. 3 times 3 is 9. And now I can see, oh, wait a second. That is equal to 36 times 36. So let's go back to the original question. We can say, therefore, that's what this 3 dots means. The square root of 1,296 is equal to the square root of two equal factors, 36 times 36. Therefore, the square root must be just the single factor of 36. And you can test that. Square 36, you could always test. Take 36 and square it, and you will get the exact same number, 1,296. That's how you can check that. Okay, that being said, can we do this for perfect cubes? Let's try. So now I have another huge number here, 1,728. I'm going to use the same method, but I'm trying to find what I need to I'm going to be making three equal groups this time instead of just two because I need three things being multiplied. So I'm going to start with 1,728. All right. And what is it divisible by? You could sum these up and you could find out that it is again divisible by 9, which is handy. So 9 times 192. 9 breaks into 3 times 3, and those are both prime. 192 is divisible by 3 times 64. 64 I can break into 8 times 8. And these are going to break up identical to 2 times 4, then 2 times 2. And again, 2 times 4, and then 2 times 2. So how many primes factors did I get? I have 1, 2, 3 threes, and 1, 2, 3, 4, 5, 6 twos. So let's write out my prime factorization in long form and standard form. It's repeated multiplication form. And so I got 6 twos. So I have 2 times 2 times 2 times 2 times 2 times 2 times 2. Nope, that's one too many. 6 twos. There we go. And then I have 3 threes times 3 times 3 times 3. And if we look at this, can I break it into three equal groups? Well, just look at the primes. I have 6 twos. Can I break 6 twos into three equal groups? Yep, I can do that. I can put 2 twos in each group. Okay. Again, I'm setting up my three groups here. And I have 3 threes, so I can break that into three groups of just 1 3. So now I can set up three equal groups of 2 times 2 times 3. There we go. Now, what is 2 times 2 times 3 equal? Well, that's easy. That's going to give us 12. If we multiply it out, and now we see, oh, 1,728 is the same thing being multiplied 3 times is 12 because of how we arrange them. So we can say our final answer is therefore the cubed root of 1,728 is equal to 12. And we're done. One more example and we'll finish off this lesson. This huge number, okay, 46,656, it wants to know, is it a perfect square, is it a perfect cube, or is it neither? So let's break it into a prime factorization. This is, if you add up the digits, it is divisible by 9. Do it in your calculator and you'll get 9 times 5,184. 9 again breaks into just 3 times 3. So we're done over there. This 5,184 also is divisible by 9. So 9 times 576. 9 again breaks into 3 and 3. 576, I'm going to break it into 9 times 64. We saw this in a previous question. Again, 3 times 3. In 64, we just did it above. We get 8 times 8. Break that into 2 times 4 and 2 times 2. And again, 2 times 4 and 2 times 2. And we have a lot. This is the biggest one we've ever done, and I won't go any bigger than this. We have 1, 2, 3, 4, 5, 6 threes, and 1, 2, 3, 4, 5, 6 twos. Whew. Okay, let's write this out so we can keep track of everything. We have 46,656. And let's be careful here. I have how many twos? I have 6 twos to account for here. So I have 1, 2, 3, 4, 5, 6. And then I have 6 threes this time. 1, 2, 3, 4, 5, 6. Now, can I arrange this into, let's figure out perfect square first. For a perfect square, can I arrange them into 2 groups? Well, that's actually not too bad at all. I see that with my 2s, I can break that into 2 groups, and my 3s, I can break that into 2 groups. So I'm going to break it into 2 times 2 times 2, and then the 3s, 3 times 3 times 3, and I get an equal group over here, and all of my primes are accounted for. So this tells me, yes, it's a perfect square. Okay, it's not asking me to multiply those out. It's all it's asking me, is it a perfect square? So let's just not do extra work if we don't have to. Now, can I arrange it into 3 equal groups? Let's give that a shot. So I'm going to be trying to create 3 baskets of the same amount of factors. Again, I can do this as well. 2 times 2 times 3 times 3, and I can repeat that. 2 times 2 times 3 times 3, 2 times 2 times 3 times 3. And yes, I got all of my 2's account. I have 6 2's. I have 6 3's being multiplied. So therefore, yes, it is also a perfect cube. All right. That concludes our 2.4 lesson. So what did we do? We used prime factorizations to understand whether or not a very large number is a perfect square, perfect cube. Now, I know we could be using calculators to calculate all of this from scratch, but the idea here is we're really diving deeper into understanding how numbers are being created by factors, because later on you're going to be doing this with variables like letters, and a calculator won't be able to help you with that. You got to be able to understand how these perfect squares, perfect cubes, how to break things apart and put them back together with their factors when it comes to more complicated things like variables. All right, we'll see you in class. Have a good one.